Hey guys, and welcome back to another video on the channel. In today's video we're going to be looking at this particular integral, specifically the integral between -1 and 1 of x squared over 1 plus pi to the power of sine x dx. How on earth are you supposed to do something like this? Well, we're actually going to be creating a theorem that breaks this down into something much easier. Now, I remember my mate has showed me this video on this cool theorem, and I thought it was so cool. I wanted to try it myself on this particular integral, which I actually did in the video, which is a very good video. I don't know the name of it because my mate sent it as a clip, but it's really cool how you can solve this quite easily using this particular thing. So, it pretty much starts off with basically saying, if you integrate a certain function over a symmetrical bound, so from a to -a to a, we have a function on the top, f of x, which is even, and you have 1 plus a constant to the power of another function, g of x, where g of x is odd in this case here. So these are very important that both of these need to be, this needs to be even and this function needs to be odd, otherwise this thing won't work. So pretty much we can just start by labeling this integral I, okay? And we can start with a substitution. Let x equal -x. So that means dx equals -dx. So if I substitute that into here, I'm going to get my bounds as a, -a, f of -x on 1 plus the constant g of -x and -d of x. I can flip my bounds around and it'll cancel that negative, so we can rewrite it as the integral of -a to a. This is an even function. If f is an even function, that means f of -x is the same as f of x. So we can rewrite that as f of x up here. 1 over, and since g of x is an odd function, that means g of -x is -g of x, so we'll substitute that in as well. So we have plus c to the power of -g of x dx. So all I did was flip the bounds and it cancelled this negative out, because if you have between -a to a, you can flip that around like this and it'll be negative of a to negative positive, and then it'll be negative of -a to b, so the bounds can flip around and then put a negative sign at the front. So this is what we've established. Now this is still I that we defined up there. So what we have is I is equal to this expression here of -a to a of f of x on 1 plus c g to the x dx, and I is also equal to -a to a of f of x on 1 plus c -g dx. So it doesn't matter whether g of x is positive or negative, they're both going to be equal to I. So why don't we add these two together? So we'll have 2i is equal to, and they've got the same bounds, so we can put them in the same integral, -a to a of f of x of 1 plus c to the g of x plus f of x and 1 plus c to the -g of x. Okay? Before we can do anything, we can't add them together at the moment because they don't have common denominators. However, if I multiply this term here, the top and bottom, by c g of x, what's going to happen is that term will turn into 1, and that term will turn into c g of x. So if I do that, I'll get the integral, so 2i is equal to the integral of -a to a of f of x on 1 plus c g of x plus f of x multiplied by c g to the power of x, c to the power of g of x, over multiplying that term, that will be c g of x, and then if you go c -g of x times by c g of x, you're just going to get 1. because these exponents are going to cancel each other out, and you have c to the 0, so plus 1. Now we can add them together because they've got common denominators. So if I do that, what I'm going to get is pretty much 2i is equal to the integral from negative a to a of f of x plus f of x c to the power of g of x all over c to the power of g of x plus 1 dx. Now, I can factor out f of x on the top, so I'll get 2i is equal to the integral from negative a to a of f of x on 1 plus c to the g of x over cg to the x plus 1 dx. And you can see that cancels with that, and 2i is just the integral from negative a to a of f of x dx. Now, since f of x is even and you're integrating over symmetrical bounds, that's the same, the integral from negative a to a is the same as double the integral from 0 to a. So we can replace that there. So we have 2i is equal to 2, the integral from 0 to a of f of x dx, divide by 2, and I is equal to the integral from 0 to a of f of x dx. So, what have we just found? Well, for starters, this is also I. So if you want to evaluate an integral in this setup here, these two terms we've just found are actually equivalent. So I can rub that out and put that there as well. I is, if it's looked like this integral, it's also the same as this here. So that means the integral that we're doing has that same property. From negative 1 to 1 of x squared on 1 plus pi to the sine x dx. We can see sine x is an odd function, that is a constant, and that's plus 1. So this must be the same as the integral between 0 and 1 of x squared. So that's going to be x to the power 3 on 3, 0 and 1. Substitute in the 1 and the answer is a third. So your integral here is a third. I hope you enjoyed that quick little video, and if you enjoyed this theorem, there'll be more coming in the future. But yeah, pretty cool theorem. I did not make this. I got shown a video of this on a previous channel. I'll see if I can find it, and I might link it in the description. But anyway, I hope you enjoyed the video.